Good morning, everyone. So Today I'm glad to be here to introduce our recent works on data and methods for ultra-high resolution visual generation, which belongs to computer vision. This lecture covers the ultra-high resolution image generation, and so we have several parts here, and um, so the image generation and um, image editing, and the third part is video generation, and uh, and the last part is about a foundation architecture. So we will have these four parts today. So um, this is our lab's GitHub account. Uh, Most data sets and the codes we discussed today are open source here. So I will begin with a brief introduction. My name is Ying Tai, and I am currently an associate professor and PhD advisor at NGO School of Intelligence Science and Technology in Nanjing University. And I am currently working on multimodal model visual perception and generation. So I have published over 100 papers in top venues with about 18K citations, Google Scholar citations. So I'm also the editors for ICML, iClear, NIPS, and ECC. So I will first explain my research background, especially on the ultra high resolution generation. So as 4K and 8K devices become widespread, so the demand for ultra high resolution content is growing rapidly in film, television, um, advertising, and digital economy. So we can see the ultra high definition industry scale uh, uh, from growing from 2023 to 2030, and so the dark part is from China, and the entire number is for the global. So, which is cited from the UWA 2030 industry report. The market is growing rapidly for the ultra high resolution content. And this slide reviews the evolution of image resolution in visual generation. So when we back to uh, uh, 2014, maybe, so when um, the field progressed from low resolution GAN or DC GAN outputs. So at that time, the resolution of DC GAN may be 64 by 64. So this is very small. And then uh, to the high fidelity GAN array, like uh, the representative work maybe big GAN. So big GAN has the generates images to like 512. So that's maybe 2018. And then the resolution increases to 1K, 1K resolution. So at that time, the model becomes a diffusion model, like um, uh, imaging or imaging from Google, and stable diffusion, which may be more popular to us. So stable diffusion from Stability AI, and which is about 2022, and the resolution comes to 1K. And now, more recently, from 2024, the resolution keeps increases to 4K, uh, or even high like 8K. So the representative works are pixel art and or Sana, which are published after 2024. So this is a visual generation uh, part from the low resolution to ultra high definition image quality from 60, 64 to 4K or even higher, uh, 10 years. But there's still some challenges in ultra high resolution visual generation. So I summarize three main challenges in from the following three categories. So the first one is the difficulty in collecting ultra high resolution training data. So we know that in some so if you are collecting some, for example, just 4K images, uh, that may be not that difficult. But if you want to collect the data for image, for example, for 4K image editing, this may be very difficult uh, because typically we don't have too much paired image editing data. For example, this example. Uh, so this is an image editing task. So the left one is the input, and we hope the right one with different closes. Uh, but but apart from the closes, that should be exactly the same, like the pose, the lighting, the background. That should be the same. Yeah, but actually, we do not have too much paired data in reality. So so this is the first challenge, that collecting the ultra high resolution training data may be difficult, especially in some tasks like image editing, video editing, and second, the spatial and temporal consistency is difficult to maintain in videos. So if you are doing some video generation task, especially in ultra high resolution scenarios, so it's very difficult to maintain the spatial temporal consistency. So here are two aspects. So the first one is spatial consistency, and the second one is temporal. So we can see that. So the spatial is very spatial and temporal are easy to understand. So spatial means um, in for example, a 2D image. In a 2D image like this one. So our the generated body should be natural, should be real, right? But in this case, you can see that the girl has 3 legs, has 3 arms, right? So that's not real. That's not true, right? So this is spatial. And temporal means we have several frames. So basically, in different frames, cross frames, the the person should be the same, right? The semantics for these frames should be consistency. But you can see that in this generated 4K videos, the body should be totally very different across the different frames. So that is the temporal violates the temporal consistency. So so this is the second challenge, that maintaining both spatial and temporal consistency may be very difficult. And the third one is higher resolution and longer sequences greatly increase the number of visual tokens. So, for example, still we can take the video generation as the example. So, if we are handling the 4K video generation, so if we have higher resolution like 4K compared the smaller resolution like 1K. So in the typical VIT vision transformer, so we will split the images into small patches like 2x2, 4x4, sort of this. So if we use the same size to split the images, when you are handling larger, higher resolution, so you may have you may have a larger number of the visual tokens. So each patch can be a, a token. So when you are dealing with higher resolution, you have more tokens. And also, if you longer, so this is a spatial. So if you have longer or more frames, which means longer time. So that also leads to more tokens, right? So when we take the two cases together, we have higher resolution and we have longer sequences. That means the visual tokens will be substantially increases. That means we will have a larger training and inference cost. So that means the training or the inference will cost too much. So uh, that you can even cannot to train the model or afford the cost. So we all know that Sora 2 from OpenAI is shut down. So I think one part of the reason could be the maybe the training and the inference cost is very uh, is too is very yeah. So this slide presents the overall research framework. Uh, uh, so our work covers image generation and image editing and video generation and foundation architectures for visual generation. So I will introduce several works. I will introduce several works of our groups published in the recent 2 years. So the first one is so including Ultra HR 100K and Vince 120K and OpenVID 1 million and Luva for as video generation and DIP and L2P for the foundation architectures. So this one is for image generation. And this one is for image editing. And these two works are for video generation. And the DIP and the L2P are for the foundation architectures. So I will first introduce Ultra HR 100K. So existing public datasets often lack true 4K details and contain too few high quality 4K samples. So, which means although the previous data sets like a Pixar 30K, Authentic 4K, um, yeah, so there are some data sets for the ultra high resolution generation, but the samples in the previous data sets, uh, the details in the in the samples are not is not sufficiently rich. Uh, so, for example, this image is from the Authentic 4K, a previous data set. So, we want to we therefore we apply strict filtering along three dimensions, which we think are very important. So the first one is detail richness, which means the sample, the 4K sample, should contain uh, um, uh, rich details, uh, rich details. The second one is content complexity. So that means the sample in your dataset should be complex, not very very simple. Yeah. And the third one is authentic quality. So authentic is very important for the for vision. So we apply the strict filtering along these three dimensions. And so this slide shows a high resolution example from our ultra HR 100K. So please pay attention to the features, the eyes, and the uh, big. So these details demonstrate that ultra high resolution dataset must contain true and clear high frequency information rather than merely large pixel dimensions. So there are many 4K images in the internet, but the details and the but the details are not that good. So So this we show the statistics of this data set here that approximately 70% of the images in Ultra HR are 4K or above resolution, and uh, and and this our data set covers 22 same categories like like from nature, human, urban. So in the nature we have weather, season, forest, lake, mountain, and for the human we have people, daily life, art, travel, sports, good, and so on. So and the right figure shows that our dataset has richer provides richer image description. So what does image description means? That means so for each nowadays we are doing some multimodal generation. So it's not purely vision only. So for an image, so we may have a caption or a description. So that means if your caption for this image or your description for the image are longer. So for example, we may have in our data set we may have 110 words words for each image. But in Ascentics 4K, so most of the images may have just 30 words for the image. Longer, more words to describe this image usually provide richer image descriptions and semantics. That offers stronger semantic supervision for the text-to-image generation. So this is a comparison um, uh, uh, among several related works like High Flow, Pixel Art, Sigma, Asana, and Diffusion 4K, and ours. So this case is on a nighttime cityscape. So you can see the focus on the building ages. Yeah, the building ages. So these are the results on ultra high resolution, 4K specifically. So you can see the building ages and the lighting structures, and you can see the enlarged local regions uh, in the here. So, so our method preserves sharper and more coherent details across the large scene than the previous methods. And this is another example on the highlights the differences in local details. We compare our result with popular Sana, which is a lightweight 4K generation method. So you can see that. So we do not evaluate only the overall visual appeal, but we also examine the local details like the eye structures, and the real material realism, like this place. Yeah. And this is another result of our. Uh, we collect Ultra HR 100K, and we then use this data set to fine tune model, and the images are generated by our fine tuned model. So this is another ultra high resolution uh, uh, landscape example that demonstrates large scale scene synthesis with fine snows, ice cracks, mountain contours, and the great lighting. Uh, it illustrates how high resolution must preserve both broad composition and very small surface details across the rich entire frames. So next, I will move to the ultra high resolution image editing. Uh, yeah. So So multi-modal instruction-based editing is developing rapidly by major technology companies like Google, uh, who launched Nano Banana, and OpenAI launched 4Image, and ByteDance launched Dream. So, by the way, one of my PhDs is currently interning in C-Dream team in Beijing. So, so these great products allows users to perform like object 3D modeling, uh, but in 2D images, and the style transformation and scene modification um, through the just instructions. Uh, or you can see it's natural language. So high quality editing data are therefore essential for connecting users' intent with generative models. And existing editing models. Uh, so let's briefly introduce what is editing. So you can see that. So I have an original image, right? Like a horse, and then I want to edit. I want to edit this original image to another image. So, so currently we mainly use an instruction. So this instruction means, for example, that's a rainy weather in the background. So uh, we call this the instruction. And based on the instruction and the original image, we have an editing model, multimodal editing model, and we can output another output uh, a res, uh, we can generate a result image. So here is the result image at the 1K resolution. So this is instruction-based image editing, and we can see from the these figures. So the comparison shows that the performance will can degrade as the edit resolution arises from 1K to 6K. So you can see that at the 1K resolution, the result is fine, it's good. But when we increase the resolution to 2K, the performance is not good. And you can see that we have two rows. The first row is about the unit-based model, and the second row is about the DIT-based model. So the unit-based models may lose the object structure, and while the DIT-based models can alert fine appearance, and or lightening um, inconsistently. So scaling resolution is not a simple matter of increasing the output size. So how to address this problem? A straightforward solution is to, yeah, we can just, for example, if at 4K resolution, this is not good, okay, let's just downsampling, right? But just downsample the original image to 1K. resolution. And then, uh, we perform the instruction-based editing. So we have an 1K result, right? This 1K result may be good. And after that, we use a super resolution model, and finally we got a 4K result, right? So this is the context plus the SR model. Just this, it followed this pipeline. So, however, the high frequency information um, lost, yeah, in this part, lost in the during downsampling, which cannot be recovered reliably. And second, the super resolution part may introduce hallucinated textures like the structures and the texts. So this pipeline, therefore, cannot preserve like text, the architectures, and fine structures faithfully. Uh, so, um, so this slide compares the resolutions of existing image editing datasets. So most range from 512 and 2 pixels to approximately 1.5K pixels, and they are useful. For learning the semantic editing, but they are insufficient for supervising native 4K textures, text, and material details, because the previous datasets are low resolution and lack of high frequency details. So resolution is not the only issue. So existing datasets may also contain instructions that do not accurately describe the actual edits. So if the text, back to the instruction. So if our training data, the image editing, we have the triple elements. So the first one is the original image, and the second one is the instruction, and the third one is the GT image. If you want to train image editing model, so you have the three, you have the triplet. So here is a challenge that, or the problem that the previous editing datasets has. So the instruction and the ground truth are inconsistency. So that may lead to the inaccurate editing performance. So we can see that here are some examples that have inaccurate editing instructions, including here is an addition and um, uh, text replacement and deletion, or zoom operation like that. So For example, in this example, the instruction is just add one small pillow next to the coach. But you can see that the ground truth has uh, add two pillows. So this is not accurate. And also you can see that here the change the material of elephants. Yeah, but it just changed one elephant, but there are another elephant. So the instruction and the ground truths are not consistent. That lead to the inaccurate editing. So we propose the ultra high resolution image editing dataset WINS 120K. So WINS is designed to improve four aspects simultaneously. The first one is the resolution. So in WINS, the it's 4K, 4K uh, resolution, and the second one is fidelity. Uh, so we apply very strict filtering to achieve the higher fidelity images. And the third one is the instruction accuracy. So the data in VINS are manually checked to to ensure the instruction and the ground truths are consistent. And finally, a more balanced distribution of editing types. Yeah. So here is an example. So this is an example of our. We collect the WINS 120K data set, and then we fine tune. Also, we fine tune. We use this data to fine tune a model, and the middle part is the results of our model trained on WINS, and the left part is input original image. Like you can see that. Uh, so the instruction maybe I think is to change the original image into a pixel style, and the right part is I mean the follows the pipeline we described here. So it's a context plus the super resolution model. So you can see that the results of our model trained on VINS have clear details and accurate the pixel styles. So this is the statistics of this, and also some very specific samples for different editing types. So the left chart organizes events into local editing, global editing, and personalized generation, camera movement, and yeah. So the subtypes like addition, deletion, replacement, color, material, style, tone, text, and action. And the example, so the right part is the example grid that shows the dataset balance matters because a model should handle many kinds of edits rather than overfit to a few common operations like just addition or deletion. So here are some examples. Yeah, actually these examples are all 4K resolution. So here are the local editing like addition, deletion, and replacement this car and replace the text from 184 to 2023 and change the color, change the material, and change the action of the woman. And the second part is the global editing, like just to like change the style of the image, change the tone, and change the background of the images. And here is personalized generation, which means you should uh, subject driving, place the woman in different places. Yeah, here is yeah, place this woman in Shanghai. And the final is last one is camera movement. Yeah, we can do translation. We can do zoom in, zoom out. And here are four more example pairs that demonstrate yeah, more clear versions to demonstrate the material replacement and the pose, change the pose of the subject and add a shape, add a shape viewpoint, and finally a text insertion text. So how do we collect the veins data set? So the first source, actually we have two sources. So the first source comes from the native native ultra high resolution videos, yeah, which is real. So we use semantically similarity and optic flow motion filtering to remove identical pairs like this, and or pairs with excessive motions or semantic mismatch, um, while retaining natural real world variation and fine texture. So in this part, we collect the data from the real videos, real ultra high resolution videos. So we know that a video we have several frames. We have a sequence which contains several video frames. So we can use some models, some techniques to filtering. For example, oh, we can uh, uh, so we can use this frame as original image, and we can use that frame as the ground truth image, uh, and the instruction we can use a vision language model to generate instruction. So after that, we have the original image, we have the instruction, we have the ground truth, and all of this and all of the data are totally 4K or even higher. And the second source are consists of 95K high quality examples from external open dataset. So this part are from uh, open datasets, external. which means this part of the data are uh, synthesized to 4K. So why should we do this? Why should we need this part of data? Because the data from the real 4K data from the first source, uh, the number are relatively small. It's just 25K. And another reason is the editing types. So the editing types from the first source are relatively limited. So if you use only the real data, the real data from the first source, your model for image editing may be maybe quite limited. So we use an complementary dual source data construction strategy from the external open datasets. And here is the pipeline for the second source, for the data from the second source. And the right figure explains how different sources contribute to different editing types, like different cameras, actions, tone, edition, text from different sources. So, so the high quality data are not obtained by a simple aggregation. Uh, so Vince uses a multi-stage filtering pipeline to evaluate the image quality. So it's just very simply to filter the data from the real videos or the external open datasets. No, actually we have a multi-stage filtering pipeline to evaluate the image quality, the instruction consistency, and the editing effectiveness. And here are the details for the different stages. For example, in the stage of data curation, we filter the data that have duplicate content, broken files, too small files, abnormal aspect ratio. And in the second part, uh, we filter according to the clarity of the image, the texture, the saturation, luminance. In the instruction part, we use also you can see here we use different VRM models to check the instruction consistency. And in the authentic assessment, we use the line authentic predictor and RT-Muse authentic predictor both to as a filter. Finally, we apply a faithful super resolution model to enlarge the data from the signal source to 4K resolution. So the complete process required 26K GPU hours. So if you do not have too much GPUs, this work maybe cannot be done. Yeah. So this illustrates the computational cost of the entire dataset construction. And here we compare Vince with the previous datasets, like including any any edit and X to edit. So the distributions show that improvements in, you can see that syntax larger means better, larger number means better, and clarity distribution. So also larger number means better. So the purple distribution is from our data set, and this is the texture distribution, and this is luminance, and this is saturation, and this is the instruction length. So here, um, data quality is evaluated from different several dimensions, including aesthetic scores, structure, clarity, and texture richness. Uh, yeah, texture richness. So for example, this is a small number means less richness, and the larger number means richness. And also exposure balance and color realism and our Artemis aesthetic assessment. Yeah. So here are some examples in our dataset. uh, uh, so this example replaces the original garment with a flowing skill dress, a silk dress. So the main evaluation criteria are the realism fab, of the fabric and folds, while the person's identity, the pose, the background, and the illumination should remain stable. And this example replaces a person with a robot. This is person to a robot performing the same exercise. So the example tests whether a subject replacement can preserve the pose, the original pose correspondence, the scene geometry, and and the overall composition. And this example, um, uh, this example, we can see that the poles are different. Poles are different, but the stability of the facial features like the rain and the tattoo. Uh, So these parts should be, and the hair, the skin tone, and the clothing and background should be consistent. And on Vince 4K evaluation benchmark, our method leads on multiple metrics. In particular, the PFID here. Metric which reflects the image quality and texture detail improves by 28%, 28% over the closed source C-Dream model. So we also compare our model with the C-Dream, which is a closed product. And this result indicates a clear advantage of Vince in preserving ultra-high resolution details. And here are some more comparisons show how adapting Queen model from Alibaba with the adapted model trained by our data improves like object replacement and the nighttime scene conversion. So the first one is the object replacement. Yeah, so there's so the enlarged, you can see the enlarged boxes. Focus attention on the stone line geometry. Yeah, so here is the original model crane. The stone line is not good, and here is our our result on 4K. And and the second case is focus on the small sign details. So you can see that in this part in the original image is very small, and in the original Queen model, the number like 16, 24 uh, are just degraded. But in our model, the numbers are correct. So this example converts an urban street image into a watercolor style. So this is a case for on global style editing. So a global style editing should affect the entire appearance while preserving the scene layout and the vehicles, the buildings, and texts as much as possible. Yeah, so we compare our model with previous editing models like any edit, step edit, IC edit. So in these previous models, they cannot preserve the texts well. And this slide demonstrates substantial sequential editing. So we call that multi-turn editing. Multi-turn editing. So this is an example. The first row is the results of our model, and second row is the results of context, flux context. And we have three turns here. The first turn is to add a butterfly shaped kit to the sky. So this part. And second one is simulating the golden sunlight at sunset on sunset. And the third turn is to change the image into a ukiyo style. So the multi-turn editing means each new instruction must be satisfied without removing the successful edits from the earlier turn. So that means for example, the turn 2 image, the turn 2 result should be based on the result from the turn 1. And here we evaluate edit types outside our training distribution. So here we illustrate two kinds of out of domain edit types. The first one is a hybrid. Is a hybrid transformation, and the second one is object extraction. So in the first one, in the hybrid transformation, that means there are two instructions in the prompt. So you can see that. So the first instruction is to transform the wolves into black. This part into black, right? And the second one is to replace the snow with sand. So there are hybrid instructions in just one prompt. And the second one is to the object extraction. So the proposed method is shown preserving recognizable structures and cleaner boundaries. So illustrating the importance of generalization to unseen instruction types. So I will now move to the video generation part. So this roadmap links data and model development over time in our group. So here is the first. Here is our first work. Our research begins with OpenVID 1 million. So you can see that the left video. So OpenVID 1 million is for high quality video data, but the motion is not good, and the instance attributes are not good. So next, we developed proposed instance cap. So instance cap improves instance attributes. So the prompts for the videos are five colorful parrots are patched on a tree branch. So you can see in OpenVID 1 million, you can see in OpenVID 1 million, the number of the parrots is wrong, But in instance cap, the number is correct. And third, we propose OpenVID++, which for high quality, which increases motion quality. So So here is OpenVID++. You can see that the motion becomes better than OpenVID 1 million and instance cap. And finally, we propose Louver this year in ICML. So you can see that the Louver pushes the generation into the ultra high resolution level. So this slide shows how successive contributions solve different parts of the video generation problems. So first, we introduced OpenVID 1 million. OpenVID 1 million was motivated by the limitations in existing video datasets. So we began to work on OpenVID 1 million just after Sora is released. In I think it's 2024 February. So after we saw Sora released, we think we searched the video datasets at that time. We found that the public video datasets are not good. For example, OpenVID, WebVID contains low-resolution videos and watermarks. And Panda, 70 million, which actually is very large, is very large. But Panda includes short captions, static clips, and abnormal motion. And other datasets are limited by restricted domains, such as Celebrate VHQ, which is just for human. So compared with these previously popular video datasets, OpenVID 1 million is positioned as an accessible dataset designed to improve these dimensions simultaneously. So OpenVID 1 million, we emphasize clearer and more aesthetically pleasing videos and richer descriptions. So unlike short generic captions, detailed descriptions cover subjects, actions, clothing, environment, and lighting. So providing more precise for semantics for text-to-video generation. And in OpenVID, we use a two-stage processing pipeline, including the first in stage one. In stage one, we have the authentic scoring, time consistency scoring, and movement ranging scoring or filtering, and and in stage two, we filter with the clarity, and then we split the video clips, and finally we do the video captioning. So here are the more detailed pipeline and the tools and the computation resources and the processing times and some other details. And the complete pipeline required 22K A100 GPU hours. So showing that the large-scale video curation requires substantial systemic systematical computation. So actually, OpenVID 1 million is the first data work in our group. And we compare OpenVID 1 million with the major test video datasets. And OpenVID 1 million reaches the million sample scale, while OpenVID HD high definition contains approximately 433 K videos at a high resolution, high definition resolution. And we further propose OpenVID++, which has more dynamic data and better results. So here are some examples. These are the motorcycle, the running horse, and the moving truck examples represent strongly dynamic scenes. And this kind of data help reduce the tendency of video models to generate static or low motion video contents. And we also compare the model trained by OpenVID++ with the baseline model Conga Video X 5 billion. So here are the illustrations. The motorcycle sequence tests subject structure, motion, posture, and viewpoint stability and consistency across videos. And here are the another examples for the running horse, which focuses on the locomotion and the dust interaction. And I will now introduce Louver, a latent cascaded ultra-high resolution video generation model with dual frequency experts. So here is the demo. So this demo includes the results also. So here the videos are all generated by our Louver model. The Louver is not a dataset. It is actually a ultra high resolution video generation model. Okay. So direct ultra-high resolution video generation involves three major challenges: the motion modeling, the semantic planning, and detail synthesis. And a successful model must generate correct content and coherent motion while maintaining the stable high-resolution details. So here are the visual comparisons show base results and 2K result and 4K result for facial makeup and a child at the table. So we emphasize that the ultra high resolution generation should not merely sharpen an image just like a super resolution model, but it should create semantically coherent and content faithful detail at a higher resolution. And Louver consists of three collaborative stages: the low resolution motion generation, video latent upsampling, and high resolution content refinement. So this staged design separates motion and resolution enhancement and the detail recovery reducing the burden of solving motion and 4K details simultaneously in just one model. And this slide compares three upsampling strategies. The pure interpolation, latent interpolation is fast, but may create artifacts. And the RGB interpolation requires expensive decoding and re-encoding. And the last one is our proposed latent upsampler aims to combine efficiency with better visual quality. And the Louver introduces a low-frequency expert at the high noise stage. So if you know a diffusion model, in a diffusion model, it has several steps from a clean image to a noise image. So in Louver is a diffusion model. So the low frequency expert is introduced at the high noise stage, and we also introduce a high frequency expert at the low noise stage. So the low frequency expert focuses on the global semantics and the structure. And the high frequency expert refines textures and edges and the local details. So here are the results of Louver. So because of the time, we skip this part. And finally, we will briefly discuss the design of the foundation architectures, especially for the diffusion models. So diffusion models face an inherent trade-off between generation quality and computational efficiency. So latent diffusion model, just like, for example, stable diffusion or flux or queen image or Z image. So these popular diffusion models are all latent diffusion model. Are all latent diffusion models. So the latent diffusion reduces cost through a VAE, a variational autoencoder, through the VAE. But it may lose some details because it from entire image to a compressed representation. While the pixel diffusion model, which is more popular, which is becoming more and more popular in recent years. So in pixel diffusion models, it directly models fine details, but require much more computation. Yeah. So we propose DIP, which is a pixel diffusion model. So DIP is introduced as an attempt to obtain the pixel level quality efficiently. So this example, these examples show that a pure DIT structure. Pure DIT structure struggles to reconstruct local details even when overfitting to a single image in pixel space, this line. And its feature clustering also shows only moderate semantic separately. So this suggests that the global modeling, so we know that in DIT, in transformer especially, in transformer, because of the self-attention design. So the global modeling is very good. However, the transformer architecture ignores or it does not explicitly to model the local part. So, this suggests that the global modeling only in DIT architecture is insufficient for local texture reconstruction. So this motivates us to combine the local modeling and global modeling with the local inductive bias together. So to address this issue, we propose DIP, and we just add a very simple patch detailer head here, which explicitly models local information, and that allows global structure and fine texture to be learned jointly. And the right part is the efficiency and quality plot. Positions DIP as here as achieving a favorable trade-off among FID, the metric, and the latency and the model scale. And we several candidate detail head. The patch detail head can be designed in different structures, in different architectures. So we compare different designs here, and including the MLPs, the attention, and the convolutional unit structure. So we finally use a convolutional structure for local refinement because convolution provides locality and translation equivalence. And these inductive bias are effective for denoising textures and edges, and while the additional parameter and the computation cost is remain limited. And we also compare different ways to integrate the detailer head. So we finally we adopt a post hoc refinement strategy, which places the local refinement module after the DIT. So this avoids modifying the internal structure of DIT and makes the design easier to combine with existing backbones. We will illustrate the advantage of this design in L2P. So, these results show the clear advantages of DIP at both 256 and 512 resolutions. And the comparison considers the several metrics like FID, inception score, latency, sort of, and which demonstrates a favorable balance between of DIP between the generation quality and the computational efficiency. The latency means the efficiency. And here are the qualitative gallery results. DIP can generate diverse objects like dogs, cats, flowers, hamburgers, cards, and it also demonstrates that DIP can synthesize both global composition and fine local texture across a broad range of content. Yeah, but in DIP, we actually just implement the class to image, which means you input, for example, a cat to the model, and the model will generate generate, for example, a cat. Where's a cat? No cat, dog. For example, a dog. So you input a dog, which is actually a class. The DIP receives the dog class and generates a dog. However, DIP cannot do, for example, a cat playing with a ball. Yeah. So actually, DIP cannot do this, which is actually the text to image. So, recently we explore following work named L2P. So L2P is actually for text to image, but L2P builds on top of DIP. So the centric idea of L2P is to fine-tune existing latent space model, for example, the image, or flux, or queen image. So into fine-tune an existing latent space model into a pixel diffusion model, moving from latent space, so here is the latent space to the pixel space. And instead of training ultra high resolution pixel model from scratch, which is very, very expensive. So the architecture reuses the transformer backbone and adds a detail head, which is actually built on top of the IP. Aims to preserve semantic capability while gaining pixel level fidelity and practical training efficiency. And L2P can be trained on a 24 GB GPU and supports efficient ultra high resolution text to image generation. So here are the pipeline of L2P's progressive resolution curriculum training details. So the details I will not dig deeply into the details. So if you are interested, you can go to this project. We have already open sourced the L2P, the codes, the paper. So if you are interested in this work, you can go to the repo. And here we summarize the data construction and the efficiency of L2P to So the synthetic or model-generated supervision can establish the 1K stage, which means when you use L2P to train a 1K model, you don't need a single real image. But the Ultra HR 100K supports the 4K adaptation training. And the latency and the memory charts show the practical benefits of maintaining a fixed token count and using a lightweight progressive design. And actually, you can see that at 4K resolution, the inference is accelerated by 98% compared with the source latent model, the image. And the time is reduced from the 51 seconds to just 1.2 seconds. And here are the performance. Yeah. So here are some quantitative results and qualitative results, and you can see that this is a bird. Yeah. And I can see. So this portrait comparison evaluates facial realism across different previous 4K models. The enlarged final portrait highlights the skin texture, the winkers, the hair, and the expression and lightening, all of which are sensitive indicators of ultra-high resolution generation quality, while the previous 4K models are generate smooth images. And here is another. Here are the another two another results. The dessert and fox examples. And yeah, I will conclude this with 3 points. So first, we construct the high quality data sets such as Ultra HR 100K and the VINS 120K and the OpenVID 1 million through carefully designed the data pipelines. Yeah, and second, Louver improves the video generation through latent cascading and dual frequency experts. And third, the DIP and the L2P enable more efficient pixel level ultra high resolution generation. And here are some QR codes linked to OpenVID 1 million, Louver, and the DIP L2P. So the codes, the datasets, and models are all open source. And yeah, and thank you very much. Yeah.
I have a question about video generation. Like we all know that currently we cannot generate very long videos because even if try to apply something like rolling KV cache or like that, we still have the problem that of error accumulation in the video, and like even if you use rolling KV cache, probably from 30 or maybe 40 seconds, the video is just like a trash that accumulate too much. And what do you think will be the key thing that will enable longer video generation?
Yeah. Yeah. Actually, we have a work. Yeah. Let me find that. Yeah, I think your question is about the arrow accumulation along the sequence. It becomes long and long, right? So actually, we have a work. We have a work. Sorry, this is written in Chinese. Yeah, this is for another project. So actually, we have explored a work which is published in CVPR 2026 this year. So in this work, we actually is based on the diffusion, autoregressive diffusion models. Yeah, because autoregressive models can generate long videos, right? So in autoregressive diffusion models, we also observed your problem that you can see that. Here the red part are actually the accumulate arrows in the previous autoregressive diffusion models. Yeah, that's our observation, which is the same as your question. So yeah, and this is also a case that the previous KV cache, yeah, right, KV cache method like T cache or some other caching method. So you can see that the when the sequence gets longer, the arrows are more obvious. So yeah, so according to address this problem, we propose a method like called AR catch. Yeah, AR catch. So here is the framework for our AR catch. So which has two parts. The first part is the inter-segment arrow separation. Yeah, yeah. Let's see. This part. Yeah, this part is to reduce the acceleration arrow in the inter segment. We mean this part is an inter segment, and this part are inter segment, right? The second part is the inter segment error mitigation. Yeah, which is to reduce the arrow accumulation and progression across the segments. So here are the two key parts to address the error accumulation in autoregression diffusion models. Yeah, and yeah, actually there are some also there are some details, but I think if you are interested, you can. Yeah, the paper is released just in this year's CPR. You can just search this work. Yeah, yeah. Thank you.
Thank you for the presentation. During your presentation, you several times mentioned that you want to increase the detailization of the image you generate with it. And how do you evaluate this detailization? Do you do it locally or for full image? And how do you benchmark it with other models?
Sorry, I'm not. Yeah, can you say that question again? Yeah, I don't understand. Sorry.
During your presentation, you multiple times mentioned that you want to increase the detailization of the images you generate.
Yeah, I want to increase what of the generated images. Sorry, I can't hear clearly.
Detailization. During your, like this? Что? Like, вот так?
Sorry, I can return to my the previous.
During your presentation, you mentioned several times that you want to make your generated images more detailed.
A detail.
Yes.
Oh, okay. Yeah. Yes. We want to make our images detail. Yeah.
How do you evaluate this detailization level?
How can I evaluate the details we generated in the results, right?
Yes.
Yeah. Okay. Yeah. Yeah. Thank you for your question. So, yeah. Actually, you have several aspects to evaluate the details, right? So if you want to ask if there is any single quantitative metric just to directly to estimate the details, I think this is we may not find that metric. Yeah, but you can, for example, you can from some popular metrics like FID, which measures the degree of natural or realism of the images, right? So if your images are more realism, just like the distribution of the real images, I think the details should be rich, right? So this is I think it's an implicit way to measure the details of the images quantitatively. This is and the other way is to from the human evaluation, right? So to human, we can easily justify or evaluate the which one it contains more details. So yeah, so I think that's the common ways to evaluate the generated result.
Thank you. And these metrics, they evaluate general detailization of the image, or they do it locally for some regions of the image?
Yeah, this is also a good question. So actually, many, for example, the FID or LPIPS or inception score, that's calculated based on the whole image, right? So there are also some metrics that compute the local part, local details. Yeah, I think so. I think PFID is that metric to put more weight on the local parts. Yeah,
Thank you.
yeah. Thank you very much.